We begin this series of videos on the Arm64 assembly language with development environments, starting with the Raspberry Pi 5 SBC with Raspi OS version Trixie. We launched the terminal, and this first environment is for programming on real hardware. We will use the GNU tools to assemble and link the programs. We enlarge the text size of the terminal to improve visibility, then we list the contents of the folder, and finally, we run nanotest.s. In the file, we write the global directive followed by the start label, which will help during execution to indicate the start of the program. Then we write the start label followed by a colon, and in the next line, which will be the first instruction, we write mov x05. This instruction moves the value 5 to the x0 register. In the following videos, we will expand on the instructions, but for now, we are just testing the environments. Now, we write the instruction mov x893, then the instruction svc0. This makes a system call or supervisor call to the operating system. In our instructions, we separate the first instruction as an assignment action and the second and third together as another action, the exit. We list the contents of the folder again and see the new file exists. Then we assemble with the GNU command as with the parameter test.s. Then the parameter -o and the object file name assembled without issues. Next, we link with the ld command with test.o and output to test. It also linked without issues. Then we need to run the program with point diagonal test, followed by a semicolon, then echo with $ and question mark. When executing with echo assistance, it should print the value 5, which is the return value we wrote to store in the x0 register in the assembly program. The second environment is with QEMU. We download the official Raspi OS image from the website, go to Software, then to Raspi OS, and download Legacy Lite 64-bit. In the description, you will find the link to this guide to run Raspi OS with QEMU. We download the DTB files and the kernel file from this repository. We leave the 3 files in a folder, for example, Raspi OS. We list the folder to verify. Then we install the QEMU base and QEMU-system Arch64 packages. If you're using a different distribution, the equivalent packages should be used. Now extract the image from the downloaded file using the xc command and -d. After relisting the contents, we see the xc file was replaced by an img file, which is the image that QEMU will use, otherwise, it would not work. We notice the image is 2.6 GB, but Raspi OS expects 4 GB. We run QEMU-img with the resize parameter, the image name, and the size 4G. Now we put the command QEMU-system Arch64 with the necessary parameters. It will start loading the system, and a QEMU window with 4 raspberries will appear. Raspi OS does not have a conventional installer, but the image itself is responsible for loading the system. However, it does detect the first login for configuration. We go back to the QEMU window and see the configuration has started in a text style format. It asks us to select the keyboard layout and we choose the appropriate one. Then it will ask for the username and password to log into the system, and also to confirm the password. Once entered, we see the terminal continues loading. Next, the QEMU window asks for the login and password. We enter the credentials we just configured to log into the session and list the contents. We see there is nothing loaded, which is normal. We proceed to write the same example from the previous environment using the nanotest.s command to edit. Next, we write the global directive, then the start label, then mov x05 to assign the value to the register, now mov x893. Then the svc0 instruction to make the system call. We assemble the program with this command with test.s and output. It assembled without issues. Then we link with the ld command with test.o and output to the executable file test. It linked without issues. Now we need to run the program with point diagonal test, followed by a semicolon, then echo with $ and the question mark. When executing with echo assistance, it should print the value 5, which is the return value we wrote in the assembly program. We have finished testing in this environment. Now we need to properly shut down the system and wait for the process to completely finish. Now it's time for the Android environment. From any Android phone, we can search for the UserLAnd app in Google Play. Check the description. We proceed to install and wait. UserLAnd is an app that runs Linux environments without using root on the phone. It includes various distributions. We run the app, see the different distributions that can be run, and also separate applications that smoothly run Linux on Android. We select Arch Linux, and it asks us if we want to use the terminal or a desktop environment. We select the terminal and wait for the installation. UserLAnd is an open-source application that allows running several Linux distributions such as Arch Linux, Debian, Ubuntu, and Kali. At this point, the app has a rating of 4.8 stars with more than 1 million downloads and has great reviews. After it finishes, we see the terminal. We proceed to write the same example from the previous environment, run the editor with the nanotest.s command. Then we write the global directive. Next, we write the start label followed by a colon. Then we must write the instruction mov x0, 5 to assign the value 5 to register x0. Now mov x8, 93 followed by the instruction svc0 to make the system call and exit the program correctly with no errors. Then we assemble the program with the GNU as command with test.s and output with -o and the object file name test.o. It assembled without issues. Then we link with the ld command with test.o and output to test. It linked without issues. Then we need to run the program with point diagonal test. We put the semicolon, then echo with $ and question mark. When executing with echo assistance, it should print the value 5. Then we exit the app. The fourth environment is through QEMU-user, which is a specialized version that only emulates the user space, not the entire system. We install the necessary packages. These are Arch64 Linux GNU by Noodles and QEMU-user. These names are specific for Arch Linux. If using another distribution, use the equivalents. We run nanotest.s. We write the global directive followed by the start label, which helps during execution to indicate the program's start. Then the start label followed by a colon, and in the next line, we write the instruction mov x0, 5 for assigning a value to the register. Now we write the instruction mov x8, 93, then the instruction svc0. This makes a system call to exit properly and return control. After exiting, we assemble with the Arch64 Linux GNU as command with test.s. Then the parameter -o and the object file name, it assembled without issues. Next, we link with the Arch64 Linux GNU ld command with test.o and output to test. It linked without issues. Now we need to run the program. We write QEMU Arch64, then point diagonal test, then semicolon, and then echo with $ and question mark to print the return value. When executing with echo assistance, it should print the value 5, which is the return value we wrote in the assembly program correctly and successfully. The fifth environment is also QEMU-user, but focused on Debian or Ubuntu. In this case, we use Emacs Linux based on Debian. We install the necessary packages. These are by Noodles Arch64 Linux GNU and QEMU-user. These names are specific for Debian and Ubuntu. In the case of other distributions, use the equivalents. Emacs Linux just released version 25 based on Debian Trixie. We wait for the download and installation to finish. Then, we list files and see it's clean. We run nanotest.s. We write the global directive followed by the start label. Then the start label followed by a colon, and in the next line, we write the instruction mov x0, 5 followed by mov x8, 93, then the instruction svc0. We save and exit to list and see the new file. Now, we assemble with the Arch64 Linux GNU as command with test.s. Then the parameter -o and the object file name, it assembled without issues. Then we link with the Arch64 Linux GNU ld command with test.o and output to test. It linked without issues. Now we need to run the written program. We write QEMU Arch64, then point diagonal test, then semicolon, and then echo with $ and question mark, which should print the value 5. We exit and shut down. We have presented 5 development environments from real hardware to emulators and virtual environments. If you liked it, give a like and subscribe. See you next time.